Very good morning, students.
Good morning, sir.
Good morning, sir.
Morning, sir.
Good morning, all of you. So there was an urgent meeting. That's why the class has been delayed by 15 minutes or so. Sorry for that. We'll start with the discussion now. So last class, if you remember, we were discussing about the substitution reactions, like a nucleophilic substitution reaction SN1, SN2, and SNI we have discussed. After that, we have started with the electrophilic substitution reaction. In the electrophilic substitution reaction, we were discussing about which type of compounds generally undergo electrophilic substitution reaction. It is a benzene and derivatives of benzene, where the pi electron instead of benzene is going to attack the electrophile first. Whatever the attack is going to happen, that will be deciding by the type of substituent present on the benzene ring. If you have electron donating group increase the electron instead ortho and para. So electron donating groups are ortho para directing, whereas electron withdrawing groups are meta directing. Among ortho and para, which will be major generally? Para will be generally major because of less steric repulsions, but ortho will be major in case of intramolecular hydrogen bonding. And if you talk of rate towards electrophilic substitution reaction, phenyl ring connected with electron donating group. Like electron donating group is a substituent, no substituent, electron withdrawing group is a substituent. Wherever we have electron donating group as a substituent, there we will be having greater rate for electrophilic substitution reaction because it increases the electron density. Wherever we have electron withdrawing group, there we have lesser rate because it decreases the electron density of benzene ring. Electron donating groups like OH, CH2 minus, O minus, NH minus, NH, CO, CH3, NH2. Electron withdrawing groups are all these CH2 plus, C double bond OH, C double bond OH. And example is haloarenes or ortho para directing, but they have less reactivity when compared to benzene. This is very important. When you look at the haloarenes, we all say that for the halogen, inductive effect is dominant when compared to mesomeric effect. Inductive effect is dominant when compared to mesomeric effect. But the lone pair of electron present on halogen, they were still in resonance with the pi electron density. Because of that, the direction of the electrophile will be towards ortho and para positions. The electrophile is directed towards ortho and para positions. But if you look at the rate of electrophilic substitution, as the net effect is electron withdrawing, it will have lesser rate when compared to your benzene or no substituted benzene. Yes or no? No substitution present on the benzene when compared to that haloarenes, they will have lesser rate towards electrophilic substitution reactions. And we have discussed about Friedel-Crafts alkylation. In that perspective, benzene react with the CH3, CH2, CH2Cl in the presence of AlCl3. AlCl3 is a very good Lewis acid. So what happens? In this case, AlCl3 is a good Lewis acid. AlCl3 will try to pick up the chlorine to form AlCl3 plus Rx. The halide ion will be attacking with aluminum to form R plus and AlCl4 minus, RCl you can say. This R plus is a carbocation which can undergo rearrangements. Which can undergo rearrangements. The R plus is a carbocation which can undergo rearrangements. So we have CH3, CH2, CH2 plus that can undergo rearrangements. This carbocation is going to be formed whenever you take AlCl3. But when you take FeCl3, the pi electron density attacks, then only FeCl3 will take up the electron density to form FeCl4 minus. So that's what we mean to say. In case of FeCl3, SN2 attack of pi electron density occurs first on alkyl halide, which generates FeCl4 minus. That means the carbocation is not obtained. That means the rearrangements are not possible. Is that clear, students? Is the discussion clear to everyone? This is a summary we can say of what we have discussed in last class.
Yes.
Yes, right. So let us talk of different other reactions after this Friedel-Crafts alkylation. We can also have acylation. What is acylation? Friedel-Crafts acylation. These are all the examples of your respective electrophilic substitution reactions. These are the examples of electrophilic substitution reactions which are undergoing by aromatic compounds like benzene and its derivatives. Friedel-Crafts acylation I'm going to discuss. In the Friedel-Crafts acylation, we will talk about taking the toluene. Yes or no? If I consider toluene and try to do toluene, I have taken this toluene I am treating with respect to CH3, CH2, C double bond or Cl. in the presence of AlCl3. Toluene I have said, so I have to substitute with CH3. Toluene treated with CH3, CH2, C double bond or Cl in the presence of AlCl3. What is going to happen? So what is the product? As I have told you, there are two steps. Step 1, generation of electrophile. Step 1 is generation of electrophile. Generation of electrophile. That means obviously the pi electron density of benzene is not involved in this particular step. So CH3, CH2, C double bond or Cl will try to treat with AlCl3 to form respective CH3, CH2, C double bond or plus. That means the carbon chlorine bond, the electron density is given to aluminium, so formed AlCl4 minus. But now the important question we need to understand is this structure stable? Whatever the structure I have written here, is that stable? CH3, CH2, C double bond O with a positive charge on carbon atom.
No, sir.
No. Why, Faizan?
Because carbon is already electron deficient while attaching the
Okay.
oxygen.
So if you think of this particular structure, Faizan, the important point which you need to understand is, can I draw the resonance structure where lone pair of electrons and oxygen, they were involved in resonance with the positive charge? So if you try to write the resonance, you will get this type of structure, CH3, CH2C. Now carbon and oxygen will have a triple bond, where oxygen will have only one lone pair now. Carbon's positive charge is nullified. Whereas oxygen has seen the net loss in electron density, it will have a positive charge. Respect to resonance structure. Resonance structure. If you look at this resonance structure, is it stable or not? If you look at the resonance stabilization, in this particular resonating structure, every atom has octet electronic configuration or not. Check out this carbon, 3 hydrogens and 1 carbon-carbon bond, 8 electrons. This carbon, 2 hydrogens, 2 carbon-carbon single bond, 8 electrons. This carbon, 4 bonds, 8 electrons. Oxygen, 3 bonds and 1 lone pair, 8 electrons. So this particular structure seems to be unstable, but it is stabilized by its resonating structure. Okay. This structure,
Okay,
CH3, CH2, C double bond with a positive charge on carbon seems to be unstable to us, because that carbon already has pi electron density moving away towards oxygen. Yes or no? Moving away from carbon. So carbon is also electron deficient. Still again it has positive charge, so it will be unstable. In that manner we generally perceive the concept, but reality is different. Reality is the lone pair of electrons and oxygen is coming into forming acyl carbonium ion, which is actually stable. Okay, it is stable due to, it is stabilized. It is stable as every atom has octet. Has octet. So in that case, what we can say is, so we will be having this pi electron density CH3, and CH3 is ortho para directing group or meta directing group.
Orthopara.
Why it is ortho para directing group? Yes, Muskan, any doubts? CH3 is ortho para directing group. It is ortho para directing group because of what? Like CH3 is electron donating group because of what? Inductive effect or any other effect? Anyone? Can I try to write the hyperconjugative structures of CH3 with this double bond or not? Think of this carefully. Can I try to write the hyperconjugative structures? Look at this particular scenario carefully. I am drawing CH3 as 3 CH bonds here. This CH electron density I am bringing into the carbon-carbon double bond pi electron density that I am moving away. So because of this hyperconjugative structure or no bond resonance structures, where you are going to have negative charge will be at ortho, carbon-carbon double bond here, 2 CH bonds as it is, and this one carbon CH plus, they will be having no bond. This is nothing but hyperconjugative structure or no bond resonance structure. You move away, that is pi electron density and negative charge. Again, try to write the resonance. You will get negative charge at para, double bond positions are changed, C double bond C, CH bonds and CH plus. Again, you try to draw negative charge coming into pi electron density moving away. You get negative charge here, Double bond positions are like this. Double bond C, two CH bonds and CH plus. There is no bond between carbon and H plus. And finally, you can try to write down the resonance structure in this fashion, where you will be having three CH bonds. These are the hyperconjugative structures of toluene. Hyperconjugative structures of toluene. Why I am saying this? Why we need to draw the hyperconjugative structures? Because CH3 is electron donating group. Either it is inductive effect or hyperconjugative effect, it is electron donating group, right? If it is electron donating group and we think of only inductive effect, electron donating groups are what groups? Ortho paradirecting or meta directing?
Or the
Electron
paradigm.
donating groups. Electron donating groups are ortho paradirecting. Why?
Because they increase electron density at ortho and para.
Yeah, because they increase the electron density at ortho and para positions. Now think of CH3 as electron donating group only of inductive effect. Where the electron density will be high, at ortho position or at para position? Because inductive effect is distance dependent, right? Where the electron density should be high? At ortho position only it should be high. Because whenever I am trying to compare the electron, because electrophilic substitution reaction completely depends upon the pi electron density attacking the electrophile. If pi electron density or electron density is more at ortho, then the ortho substitution will be major. That is what we think. But we cannot say at ortho electron density is high. That is the perspective only if we think of inductive effect. If we draw the hyperconjugative structures, due to no bond resonance, the electron density is high not only at ortho but also at para equally. Hyperconjugation is the dominant factor, so the electron density is high at para also greatly. If electron density is high at para, I can say para will be the major product, because at para you will be having lesser repulsions. If you think of inductive effect only, you should say ortho should be major, but that is not the scenario. Para is also coming to the major, and it is all the depending upon the repulsions and depending upon the electron densities. So what you can say now is, so we have toluene and we have electron density at, and we have this type of electrophile CH3, CH2, C double bond O with a positive charge on carbon. This electrophile is stabilized because of resonating structure. This pi electron density attacks this particular electrophile. The para position is actually attacking. If the para position attacks, can I say this is A carbon, B carbon? Which carbon will get positive charge? Which carbon among A and B carbon, if the electron density present between A and B is attacking through B, which carbon should get a positive charge? Obviously the other carbon A. So that should be getting positive charge, because from that electron density is lost. And we also have AlCl4 minus in the reaction mixture. That AlCl4 minus can easily pick up the proton present here, and CH electron density can come into, because it is only stabilized. It is stabilized by resonance. It is, this structure is nothing but Wieland complex. It is stabilized by resonance. And this step is the rate determining step. And this is your toluene. The pi electron density of benzene attacking your respective CH3, CH2, C double bond O plus to form this particular intermediate, which is also called as sigma complex or Wieland intermediate. Wieland intermediate. So this particular formation of sigma complex or Wieland intermediate, that is nothing but your rate determining step. AlCl4 minus picks up the proton, that CH electron density comes into, and as soon as AlCl4 minus picks up the proton, we generate AlCl3 plus HCl back. So the Lewis acid is obtained again back. Is that clear how to produce the product? Yes or no? Important point which you need to understand is compare the rate of these two reactions. Compare the rate of CH3, or you can simply say benzene and hexatetrobenzene. This is what? Benzene. Benzene means C6H6. C6H6 and a C6D6. There was no hydrogen among these two, which will have compare the rate of C6H6 and C6D6 towards electrophilic substitution reaction. All of you try to answer very interesting question. C6H6, C6D6. Everyone understood the question or not? C6H6 is a benzene, C6D6 is hexadeuterbenzene. That means all the hydrogen atoms of benzene has been replaced by deuterium atoms now. So which will have greater rate towards the electrophilic substitution reactions.
Same rate, sir.
Why, Faizan?
Because attacking of pi electron density is the rate determining step.
Very good. Okay, they both have same rate towards electrophilic substitution reactions, because the rate determining step do not include the cleavage of CH bond. Do not include the cleavage of CH bond or CD bond. Cleavage of CH or CD bond. Everyone understood this or not? The rate determining step is the pi electron instead attacking the electrophile. In the pi electron instead attacking electrophile, the CH bond is not cleaved. The CH bond is cleaved in the next step. Like AlCl4 minus picking up the proton. That is not the rate determining step. That means that will actually happen at a greater rate. That means very fast that second step is happening. If the CH bond and CD bond do not have same energy, the bond energies of CH bond and CD bond are different, completely different. CD bond is a stronger bond. We all know that. We have explained that using the concept of reduced mass. We all know CD bond is a stronger bond, but the rate determining step is not involving the cleavage of CH bond. So that is why they are both will be having same rate towards the electrophilic substitution reactions. Clear? Very good. So let us talk about next reaction. After Friedel-Crafts alkylation and acylation, we can think of nitration. Nitration. Generally, I am discussing for just a toluene or benzene derivatives, because once you go with the different functional groups, phenol will undergo, OCH3 anisole will undergo, benzaldehyde will undergo different electrophilic. So with respect to different functional groups, we'll discuss the reactions again. So nitration means what? Nitration means treating. Okay, so let us do the reaction with toluene. Toluene treated with concentrated HNO3 in the presence of H2SO4 produces respective nitrobenzene. Produces respective nitrobenzene. If you talk with respect to benzene, it forms respective nitrobenzene. If you talk with respect to toluene, like CH3, I'll keep a substitution here. You will get NO2 CH3 para nitro toluene is going to be obtained. Para nitrotoluene. The reason here, the mechanistic approach, generation of electrophile. Step 1, HNO3 and H2SO4 both are strong acids, but when compared to HNO3 and H2SO4 is even stronger. How to compare a particular acid is more stronger? Based on Ka values. How the Ka values are obtained? Based on the stabilities of respective conjugate bases. So HNO3, you can say N double bond O, OH, structure of HNO3. And if you try to react with HNO3 with H2SO4, H2SO4 will have the structure S double bond O, OH and OH. That means what we can say, students? H2SO4 is a better acid when compared to HNO3. That means I can say H2SO4 can lose the H plus ion easily. That means lone pair of electrons and oxygen from HNO3 can pick up this particular proton. Because H2SO4 is a stronger acid, the lone pair of electrons present in oxygen, they can pick up this proton. This OH electron density can be given to oxygen. So oxygen will have only one lone pair now. Two OH bonds will be present and a positive charge. Nitrogen in double bond O. And now what you are going to have is oxygen bearing a positive charge. is not stable, and along with this we'll have HSO4 minus released out. S double bond O, S double bond OH and O minus. S double bond O, S double bond O, OH and O minus, that is nothing but HSO4 minus. The nitrogen oxygen sigma electron density that is now given to oxygen, because loss of water will happen because oxygen having a positive charge that is not stable. So we'll get NO2 with a positive charge on nitrogen and H2O. Along with that HSO4 minus is there. So whenever we have HNO3 and H2S4 added, the electrophile generated is NO2 plus, H2O and HSO4 minus are released. H2SO4 is a acid, so HSO4 minus is conjugate base. Yes or no? This is a step 1. Step 1. Step 2. We have toluene and we have NO2 plus. The pi electron density attacking from the para position. As the attack is happening from the para position, you can say NO2 formed here, and you will have positive charge at meta, and you have CH3. This is a rate determining step. Then HSO4 minus comes into the picture. It tries to pick up the proton. CH electron density comes into, and you will generate what? You will generate NO2 substitution and CH3 present at the para position, releasing back H2SO4. We are not having ortho substitution because of repulsions between CH3 and NO2. But if I take phenol, then we can have ortho nitrophenol form because of intramolecular hydrogen bonding. If I replace this CH3 with OH, then the NO2 will substitute better at ortho position because of intramolecular hydrogen bonding. And H2SO4 is released back, so it can be taken in catalytic amount. It can be taken in catalytic amount as it is released back. Clear or not, this particular reaction?
Yes.
Yes, right. Next is sulfonation. We'll discuss sulfonation and then go with the next type of reactions. Sulfonation means H2SO4 in the presence of SO3. Same toluene I am considering. Toluene treated with H2SO4 in the presence of SO3, that is H2S2O7, will form respective SO3H, CH3, SO3H. So SO3 itself will act as a respective electrophile. So we have toluene treated with SO3. SO3 will have this type of structure: S double bond O, S double bond O, S double bond O. So pi electron density attacks from the para position. As soon as the pi electron density attacks, the S double bond O electron density moves towards oxygen. So sulfur is now connected with S double bond O, S double bond O and O minus, and we have these structures CH3. And here we have hydrogen. This CH electron density is picked up by proton, and this CH electron density comes into. You will form respective S double bond O, S double bond O, OH, and we have this structure. Yes or no? Toluene treated with SO3 produces respective para substituent product, and the substitution is going to be SO3H group. Sulfonic group is actually substituted the para position, and this is going to be a respective major product. Is that clear, students? Is everything clear so far?
Yes, sir.
So these are the different types of reactions where you can understand about how the electrophilic substitution is actually happening. And then comes the next concept, like what type of next reactions we can think of after addition: electrophilic addition, nucleophilic addition, free radical addition, substitution, nucleophilic substitution, electrophilic substitution, then free radical substitution reactions. Free radical substitution. So which compounds will undergo free radical substitution reactions greatly? If you think of electrophilic addition, we have discussed about alkanes and alkynes. Nucleophilic addition, we have discussed about carbonyls. Free radical additions, we have discussed about the alkene treated with HBr in the presence of peroxides. Nucleophilic substitution, we have discussed about alkyl halide and alcohols. Electrophilic substitution, benzene and derivatives of benzene. Free radical substitution, which will undergo free radical substitution greatly? Which set of compounds? Alkanes. Okay, alkanes upon treatment with the halogens in the presence of very high temperature or upon sunlight, they will form respective free radicals, and those free radicals will be again combining with the different alkyl radicals to form respective haloalkanes. Right on that point? Alkanes undergoes free radical substitution reactions. So the general reaction would be like CH4 plus Cl2 in the presence of H mu or sunlight produces CH3Cl. Disadvantage what you can have is here we can have polyhalogenation. We can have the possibility of polyhalogenation. Right, CH4 plus Cl2 in the presence of H mu and sunlight gives CHCl. So this actually proceeds to 3 steps. Chain initiation. What happens in chain initiation, students? CH4 plus Cl2 in the presence of H mu or heating produces CHCl. Chain initiation, what happens? Can anyone say what happens in chain initiation? Try to think of this. You might have studied these reactions earlier also. All of you think of this. What happens in chain initiation? No one?
Cleavage of bond.
Like which bond is going to, what is the rate determining step? That's what I want to ask.
Formation of free radical.
So what happens in chain initiation step is simply you can just try to cleave the chlorine bond. Yes or no? I can do the cleavage of Cl bond or not? Can I do the cleavage of Cl bond? Because we have sunlight. Chain initiation step is very simple. Let me write the mechanism total. Chain initiation, chain propagation. This is step 1. Step 1. Cl bond treated with H mu. It produces respective chlorine free radicals, 2 Cl dots. Step 2. Chain propagation. In the chain propagation, what happens? The chlorine free radical, whatever is obtained, that react with the respective methane. So let us take CH3H plus Cl dot. It forms CH3 dot plus HCl. CH3 dot can react. CH3 dot can react with another ClCl, that is chlorine molecule, to form CH3Cl plus Cl dot. These reactions happen in the step 2. And step 3, chain termination. What happens in chain termination, students? Cl dot molecules like chlorine free radicals, they will combine with each other to form Cl2. CH3 dot can also combine with Cl dot to form CH3Cl. CH3 dot can also combine with CH3 dot to form CH3CH3. Yes or no? So this is nothing but your monohalogenated product. Monohalogenated product. These all can happen. Chain initiation, the chlorine, the bond between two chlorine atoms that is going to broken to produce respective chlorine free radical. Chain propagation, CH3H. CH3H is going to be reacting with the chlorine radical to form CH3 dot and HCl is obtained. CH3 dot react with the ClCl to form CH3Cl and Cl dot. These all happen in the chain propagation. Chain termination, the chlorine free radicals, the methyl free radicals will combine to form respective Cl2 or ethane, or CH3 can combine with CH3 dot, Cl dot to form CH3Cl. That is the chain termination steps. So now out of all these steps, what is the rate determining step? Very simple, but you can answer this easily. Try to think on this and you can answer it. Out of all these steps, which one is the rate determining step? The rate determining step is the first step of chain propagation. Like chain propagation itself is step 2. In the chain propagation, Cl dot, whatever the free radical, halogen free radical which is produced, that will try to abstract the proton, like abstract the hydrogen radical. Abstraction of hydrogen is going to happen to generate a respective alkyl radical. This is nothing but RDS. Understand this carefully. The rate determining step is abstraction of RDS. The rate determining step is the rate determining step is abstraction of hydrogen from alkane to form alkyl radical. So that means whatever the different types of hydrogens we have, whatever different types of compounds we have, whenever you try to remove the hydrogen and form a respective alkyl radical, based on that alkyl radical, based on the stability of that alkyl radical, the rate of this particular alkane towards free radical halogenation is going to happen. That is the rate of free radical substitution reaction. Free radical substitution reaction, FRSR. The rate of free radical substitution reaction will depend upon that is the rate of free radical substitution reaction will depend upon the stability of respective free radical produced. Example, if you take, like if I take CH3Cl, CH3, CH2Cl, let us take CH3, CH2Cl, CH3, CH3Cl, CH3CCl, CH3, CH3, CH2 double bond CH, CH2Cl, pH, CH2Cl. Try to compare the rates A, B, C, D, E.
Sir, can you show the previous slide?
Yes.
Done, sir.
Done. Right. Try to compare the rate CH3, CH2Cl, CH3, CHCl, CH3, CCl, CH3, CH3, CH2 double bond CH, CH2Cl, pH, CH2Cl. Try to compare the rates of these particular reactions, like rates of these particular compounds, or what I have given is alkyl halides directly given to you, right? So these are the products we need to say. So instead of products, we have to write the respective. We have to compare respective alkanes, substrates rates we have to compare. Those are the products obtained. Whatever I have written is the product obtained. And we all should agree, like this CH bond is going to be obtained easily because there you are going to produce secondary free radical. This CH bond produces, if this CH bond cleaves or the other CH bond cleaves, you will get primary free radical. In the third case, in option C, if this CH bond cleaves, you will get 3-degree free radical. In the fourth case, if this CH bond cleaves, you get allylic, and in the fifth case, you get benzylic. This is 3-degree, this is 2-degree, this is 1-degree. So 1-degree free radical, 2-degree free radical, 3-degree, 3-degree less than allylic, allylic less than benzylic. This is the increasing rate of reaction towards X2 in the presence of H mu. Yes or no? Is that clear?
Yes, sir.
Yes. Right, very good. And the next type of reaction is also we can think of NBS. NBS, what is NBS? Can anyone say?
Nitrobromosuccinimide.
N-bromosuccinimide, very good. The allylic and benzylic substitution occurs. Whenever we take NBS, N-bromosuccinimide, or NCS, N-chlorosuccinimide, okay, allylic and benzylic substitution benzylic substitution occurs when NBS or NCS were taken. NBS, NCS, NBS means NBS, N-bromo succinamide. You will have this type of structure. Okay, it also proceeds through free radical substitution reaction. It is also an example of, it also proceeds through free radical substitution. Free radical substitution. Allylic and benzylic substitution occurs when N-bromosuccinamide or N-chlorosuccinamide were taken. N-bromosuccinamide or NBS will do the allylic substitution always, because allylic free radical is going to be more stable. So the questions can be like, whenever you see NBS, you directly substitute at the allylic position. That's it. Just a second. Just okay. Right. So that means the question can be in this manner. So what you will do whenever a question has been given like this, NBS HMU. You know allylic carbons, right? I'll give the numbering. So I'll give 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. Which positions are allylic positions?
3 and 6.
3 and 6. So the substitution will happen at the third or sixth position. So this is going to be a right product. Is that clear, students? N-bromosuccinamide, you will be getting respective free radical substitution happening. So you will be getting 3-bromocyclohexanone. This is nothing but 3-bromocyclo, because I have to give numbering 1, 2, 3. Third position you have bromine substitute 3-bromocyclohexene 1 or cyclohexanone. So these are the examples of free radical substitution reactions, and they are generally undergone by respective alkanes. And this is what the mechanistic approach. In that, you have to compare the stabilities of free radicals. Yes or no? Based on the stabilities of free radicals only, you can say which free radicals are more reactive and why they are more reactive. Is that clear or not? Let us try to think of an example. The best example which you can think of is CH2. I'll compare the rates. Okay, examples include methyl benzene and ethyl benzene. Which will have greater rate? Methyl benzene and ethyl benzene. Compare the rate A and B. Rate towards free radical substitution reaction. Simplest question you can think of. Methyl benzene and ethyl benzene, which will have greater rate towards free radical substitution reactions. Which will have, students? Try to answer right or wrong. Only two options are given, no? A and B. So either A greater than B or A less than B or A equal to B. Suhani says A less than B. Why? So we have to compare the stabilities of respective free radicals. If you think of respective free radicals, what are the free radicals obtained in the first case? You will get this type of free radical, CH2 dot. In the second case, what type of free radical you will get? CH3, and you get CH dot here. If you compare the stabilities of this, the first one is benzylic free radical, the second one also is similar to benzylic. But if you look at the second compound, CH3 is electron donating group. But if you think of properly, CH3 is not only electron donating group, you can also have hyperconjugation with this free radical and this CH3. Yes or no? Only resonance. First compound only resonance. Second one you have resonance with the benzene plus hyperconjugation with the adjacent CH3. Hyperconjugation. So resonance plus hyperconjugation is there in compound B, so that should be more stable. So A less than B, that is the right answer, Swani. Very good. Okay. So this is how you can answer. You can understand this free radical substitution reaction. Different cases you will get. Only thing is you have to compare the stabilities of respective free radicals. Right, students? Then comes the next set of reactions. What are the next set of reactions after addition reactions and substitution reaction? We can also have
Elimination reaction.
elimination reactions. How many types of eliminations we have? Elimination reactions. Elimination reaction means in these reactions, what you will be having is some small compounds, they are going to be lost. Okay, simple molecules are eliminated. Generally, by the name itself, we can understand. Generally, by the name itself, we can understand. We can understand. The reactions include the loss of. The reactions include the loss of simple molecules. Simple molecules. So elimination, it can be classified into 4 types actually. Okay, elimination is actually classified into 4 types. Alpha elimination, beta elimination, 1,3 elimination, 1,4 elimination. Alpha elimination produces what? Alpha elimination means the 2 atoms which are going to be lost, they are from the same, the 2 groups which are going to be lost, they are from the same atom. Okay, the 2 atoms or groups are lost from same atom, generating, example you can say CHCl3 in the presence of CHCl3 plus OH minus, what happens? Example you can say CHCl3 plus OH minus. OH minus tries to pick up the proton. OH minus plus CHCl3. OH minus try to pick up the proton. The carbon chlorine bond is lost. So from the same carbon atom, we have hydrogen lost as well as chlorine lost. Hydrogen is lost and in the form of H2O. And the Cl minus is obtained. Along with Cl minus, we produce what? The carbon CCl2 with a free radical on the carbon. CCl2 is obtained, dichlorocarbene. Yes or no? That is actually including the elimination reaction. You can see Raman-Tiemann reaction also. OH minus picking up the proton, the carbon chlorine is lost. So the generation of CCl2, that is dichlorocarbene, which is a very strong electrophile, is actually undergoing alpha elimination. Beta elimination means like from the 2 adjacent carbon atoms, the elimination will happen. Elimination occurs from 2 adjacent carbons, and this is what we study in our syllabus: beta elimination, E1 elimination, E2 elimination. 1,3 elimination forms 1,3 diradicals, and they can combine to form cyclopropane also. 1,4 diradicals are obtained, and cyclobutane can also be obtained. Cyclobutane, like on the first and third position, 1,3 eliminations, 1,4 eliminations are not there, but just think of 1,3 elimination means on the first and third carbons we have lost. So what they can think of is they will form respective diradicals, and those diradicals can also combine to form respective cyclopropanes. 1,4 elimination, they can also lead to the formation of cyclobutane, and if it is conjugated, okay, in the case of conjugated system, you can have okay, in this 1,3 butadiene can also be formed. Like the two elements, the two groups are eliminated from the first, second, third, and fourth. That is first and fourth carbons. They have seen the elimination, so we got a radical there. So instead of forming a cyclopropane, if you have 2,3 double bond, the pi electron density you can imagine as 1 electron given to second and 1 electron given to third. So this 1 electron first and second they form a pi bond. 1 electron third and fourth they form another pi bond. So you have this type of molecule formation. Yes or no? Cyclopropane, cyclobutane. So our main concept is actually going through. Okay. Our main concept will be actually proceeding through beta eliminations. In our study, we mainly focus on beta eliminations, which are again classified in two types: E1 eliminations, E2 eliminations, and E1 eliminations. E2 elimination and E1 elimination. We also have E1CB. E1CB is elimination happening in the presence of a conjugate base. So that is also similar to this E2 only. So we'll discuss E2 elimination and E1 elimination in detail, what is actually happening, what was the stereochemistry, and all other points as well. Understood, students? That is a overview or introduction of elimination reactions: alpha elimination, beta elimination, 1,3, 1,4 eliminations. Alpha elimination is useful whenever we actually form a respective dichlorocarbene. Beta elimination is again classified as E1 and E2 eliminations. So we'll discuss E1 elimination and E2 elimination. That is our main point of study as far as 12th standard is considered. 1,3 eliminations, 1,3 diradicals, diradical chemistry, 1,4 elimination, 1,4 diradicals. That is not there in your syllabus. You don't need to worry, but just think of they will be forming cyclopropanes and cyclobutanes. And if there is a conjugation, they form butadienes as well. So let us start with E2 and E1 eliminations. First one is E2 elimination. E2 elimination. E2 elimination, you have to know the name. What do you mean by E2 elimination? E2. E2. 2 stands for
Bimolecular elimination.
bimolecular. E stands for elimination. Bimolecular elimination reaction. Bimolecular elimination means rate depends upon what? So substrate
And
plus base gives products, let us say, and rate of the reaction should be directly proportional to concentration of substrates as well as concentration of base. So rate depends upon both the concentration of substrate and concentration of base. So order is equals to 2 and molecularity is equals to 2. Molecularity is equals to 2. And this type of reactions, bimolecular elimination reaction, depends upon the rate of bimolecular elimination reaction depends upon concentration of base. Can I say stronger bases will undergo E2 elimination? Yes or no? If we have a strong nucleophile among SN1 and SN2, which will happen? SN1 reaction, rate of SN1 reaction is directly proportional to concentration of substrate only, because formation of carbocation is the rate determining step, not the nucleophile attacking the carbocation. So rate of SN1 reaction is not depending upon the concentration of nucleophile. Rate of SN2 depends upon concentration of nucleophile. So if you take a strong nucleophile, it preferentially undergo SN2. Yes or no? Similarly, E2 elimination rate is depending upon concentration of base. So E2 elimination will only happen in the very strong base conditions. Okay. Since very strong bases like alcoholic KOH, NaNH2, tertiary butoxide, alkoxides. Very strong bases like alcoholic KOH, NaNH2, tertiary butoxide, alkoxides will undergo or will be used as reagents in the E2 elimination. Will be used as reagents in E2 elimination. So let us take an alkyl halide. Okay. Generally, alkyl halides will undergo elimination reactions, E2 elimination, E1 eliminations. So let us take an alkyl halide and understand how the elimination is going to happen. Let us consider an alkyl halide. Let us consider an alkyl halide and perform E2 elimination. Because to write more facts about E2 elimination, like I'll be giving 3 different types of alkyl halides, primary, secondary, and tertiary, and ask a question among primary, secondary, tertiary, which will undergo E2 elimination greatly. What is the rate? Like primary alkyl halide, secondary alkyl halide, tertiary alkyl halide I have given. If I ask primary, secondary, tertiary, SN2, what is the order?
Primary greater than
Immediate
secondary.
secondary greater.
Primary, then secondary, then tertiary. Reason? Based on steric repulsions, you can say. Yes, very good. SN1 reaction, what is the rate? Primary, secondary, tertiary.
Tertiary greater. Tertiary greater
Reason?
secondary.
Reason?
Formation of carbocation.
Carbocation,
Gradient
very good. Carbocation based on the stabilities of carbocation. Now let us consider alkyl halide like same primary, secondary, tertiary alkyl halide, and I am doing E2 elimination. Which is more reactive, primary or secondary or tertiary? To answer this, we have to know what was the mechanistic approach. Yes or no? So let us consider alkyl halide CH3, CHCl, CH2, CH3, and treating with OH minus. Let us understand this particular reaction. So what I am trying to say here is, students, we have carbon chlorine bond, CH bond, CH2 groups are there here. Now OH minus has to pick up the proton. This is alcoholic OH. Alcoholic OH means OH minus in the alcoholic medium acts as a very strong base. So OH minus has to pick up the proton. So which is the acidic proton that we have to figure out? So for that, I can say carbon chlorine bond, that is going to be polar bond, because chlorine is more electronegative when compared to carbon. So it will develop partial negative on chlorine, partial positive on carbon. Partial negative charge developed on chlorine, partial positive charge developed on carbon. So because of partial positive on carbon, the CC sigma electron density will move. Because of the movement of CC sigma electron density, this carbon will get delta plus plus. This carbon has developed some positive charge. Because of that positive charge, the CH electron density will move towards the carbon. Because of that movement, this hydrogen develops some delta plus charge. So OH minus can pick up this proton or not? OH minus can try to pick up this particular proton, or if you try to change the positions, okay, if you try to change the positions, CCl I am keeping here, CH2 I am keeping here. This is partial positive, delta plus plus, and this is having delta plus. OH minus is a base which is trying to pick up this proton. This reaction is happening in a single step, students, but there will be always a transition state. Even though a reaction happening in a single step, directly you cannot have substrate to product. There will be some transition state, which is known as activated state. We have studied the same in chemical kinetics. Yes or no? You will have the reactants, they will be converting into products. They have to cross the energy barrier. Properly, they have to collide, and they have to cross the energy barrier also. So in the same context, what you can say is OH minus has to pick up this proton. This CH electron density seems to be coming into this CLC carbon chlorine bond is supposed to be leaving. So we have transition state looking like this. CH3 is connected with carbon. This CH bond is as it is. This CH bond is about to be cleaved because that OH minus is developing new interaction with hydrogen. So this CH bond is about to cleave. Whatever the bonds which are supposed to be cleaved, they will have just dotted lines. That is the bonds which are going to be formed or which are going to be broken. We have to represent them with dotted lines. This carbon-carbon single bond is as it is. The double bond is about to be formed. So again dotted lines. This another carbon. This CH bond. Carbon chlorine bond is about to be broken. Again, dotted lines. And you have CCH3. So base picking up the proton, dotted line, new bond is formed. The CH electron density is going to be forming a pi bond. CH bond is broken. Carbon carbon double bond, that is pi bond, is going to be formed. Carbon chlorine bond about to be broken. So this is nothing but your respective transition state. How does your transition state looks like? Transition state looks like alkene or not? Yes or no? Because carbon carbon bonds, they are going to form a double bond. The transition state is looking like alkene. So immediately this transition state, because it is high, more electronic repulsions will be there in the transition state. Immediately that will lead to the formation of CH3 CH double bond CH CH3 with the loss of chloride ion, as well as OH minus picks up the proton, so loss of water. So the transition state looks like alkene. You get this type of alkene. Everyone got this point now or not? Let us consider an alkyl halide and perform E2. If you try to perform E2 elimination, the transition state, how does it look like, students? The transition state is looking like an alkene. If the transition state is looking like an alkene, and I'll give three different alkyl halides to you now. I'll give you three different alkyl halides: CH3, CH2, Cl. CH3, CH, Cl, CH3, CH3, C, Cl, CH3, CH3. Yes or no? Primary alkyl halide, secondary alkyl halide, tertiary alkyl halide. I am not supposed to compare. I am not supposed to compare the steric repulsions, because how does your transition state looks like? You have to compare the stability of alkene to decide which is undergoing the E2 elimination at a greater rate. So if it undergoes E2 elimination, you will get what type of alkene? You will get CH2 double bond CH2. If it undergoes elimination, you get what type of alkene? CH3 single bond CH double bond CH2. If it undergoes elimination, you will get what type of alkene? CH3 CH C double bond CH2 CH3. In this alkene, like compare the stability of respect to alkene. CH2 double bond CH2, there are no alpha hydrogens, 0 alpha hydrogens. Here we have 3 alpha hydrogens. Here we have 6 alpha hydrogens. So in the tertiary alkyl halide, we have more number of alpha hydrogens or not? So primary alkyl halide, secondary alkyl halide, and tertiary alkyl halide, if you want to compare the rate of E2 elimination, you have to compare the respective stabilities of transition state. Because the transition state looks like an alkene, I form the respective alkenes. So if I form the respective alkenes, so stability of alkene is directly proportional to number of alpha hydrogens. Therefore, E2 rate will be 3 degree greater than 2 degree greater than 1 degree. Everyone understood this point or not? The 3 degree alkyl halide will be undergoing greater E2 than 2 degree. The 2 degree will be undergoing greater E2 when compared to 1 degree. That is the rate of E2 elimination. That is the rate of your respective E2 elimination reaction. Is that clear to everyone?
Yes, sir.
The rate of E2 elimination is 3 degree greater than 2 degree greater than 1 degree because the transition state looks like an alkene. Is this mechanistic approach clear? Yes or no, Sapna?
Yes, sir.
So now the question which we need to think of is, why I am moving the carbon-carbon electron density, generating partial positive on this carbon and then CH electron density. Instead of this all movements, why can't I directly pick up OH minus? Why can't OH minus directly pick up proton from this carbon to which chlorine is connected? Because if you look at this proton, this hydrogen, in that hydrogen also we have, like in this CH bond also we have electron density. The OH minus can also pick up this proton. The CH electron density can be given to carbon. Yes or no? So this proton, this CH electron density moment is very high because it is the hydrogen directly connected to carbon to which halogen is connected. So why can't base pick up this hydrogen? If that hydrogen is picked up, you can also generating respective, you will not be generating respective alkene, but if you try to pick up this particular hydrogen, that OH minus will experience more repulsion because of leaving group also present on the same carbon. OH minus cannot pick up the hydrogen from the same carbon to which leaving group is connected. Yes or no? Because of repulsions. And you can also think of other attack. I have picked up this beta carbon only. This is alpha carbon, this beta carbon, this is also beta carbon. This beta carbon also hydrogens. Whenever we have two different beta carbons, that beta hydrogen is picked up, which will have more number of substitutions for the respective alkene. That is nothing but states of alkene. Write down that points. Base OH minus cannot pick up proton from the carbon from the same carbon to which halogen is connected, due to steric repulsions. OH minus, base OH minus cannot pick up the proton from the same carbon to which a halogen is connected due to steric repulsions. Next thing what you can think of is OH minus or base will pick up proton from that beta carbon, which will produce most substituted alkene. The most substituted alkene is nothing but shades of alkene. But there are exceptions. There are some exceptions for the above statement. Some exceptions where Hoffman's alkene is also produced, where least substituted alkene is also formed. We'll discuss those exceptions. Least substituted alkene is said to be what type of alkene? Least substituted alkene? Hoffman's alkene. Can anyone remember or say under what condition will generate Hoffman's alkene? So we'll discuss that all the cases. Okay, we'll discuss all the cases. So let us try to think of this attack. CH3 CHCl CH3 forms these two type of products. CH3 double bond CH3 plus CH3 CH double bond CH2. This is A, this is B. Which is major, which is minor? CH3 CHCl CH3 treated with alcoholic OH forms A and B. Which is major, which is minor, and why? No one can answer this. Whether he says A is major. Why A is major? Because more substitution, right? This C double bond C is a system. This is alpha carbon, this is alpha carbon, this is also alpha carbon. C double bond C system, this is alpha carbon. In A we have how many alpha hydrogens? 3, 3, 3. 9 alpha hydrogens. In B we have 1 alpha hydrogen. Which has more number of alpha hydrogens? Obviously A. So A will be major, B will be minor. Got it? Try to, and E2 elimination is always is anti-elimination. Try to write the IUPAC name. Try to write the IUPAC name of the product form. I think I have given this example also earlier. Try to name this product. Try to write the IUPAC name of the product found in this particular reaction. So E2 elimination is anti-elimination. So whatever the hydrogen and whatever the leaving group which are going to be lost, they should be always opposite to each other. So think of this particular substrate. So we have chlorine here, we have hydrogen here, we have hydrogen here, and we have methyl here. And treating with alcoholic OH or NaNH2, NH2 minus. NH2 minus is the base now. That is going to pick up the proton from where? NH2 minus is the base now. It can't pick up the proton from this particular carbon because this hydrogen and this chlorine are on the same side. On the other hydrogen, this is alpha carbon, this beta carbon, this beta carbon. So on this beta carbon, you have two hydrogens, one is above and one is below. So OH minus can only or NH2 minus can also pick up this particular hydrogen. The CH electron density comes into CCl can leave. So we'll be getting this type of compound. If you try to name it 1, 2, 3, so you'll get a 3-methyl cyclopentene or pentoenine. Okay, so you have to think of anti-elimination only. With the anti-elimination only, you will be getting right products. And try to think of this rate. Which will have greater rate. A and B. Compare now. Greater the number of hydrogens which are in the anti-direction to that of leaving group, greater will be the rate of the reaction. Greater the number of hydrogens, which are anti to the leaving group, greater will be the rate of E2 elimination. So now try to answer which will undergo E2 elimination greatly. In the compound A, methyl is down, that means hydrogen is above. In the compound B, methyl is above, that means hydrogen is below. And this is also beta, this is alpha carbon to which bromine is directly connected. Adjacent carbons are beta carbon. This is beta, this is beta. This is also beta, this is also beta. In this beta, one hydrogen will be above because they are not mentioned. One hydrogen above, one hydrogen below. Here also one hydrogen above, one hydrogen below. If you look at compound B, you have two hydrogens on the two beta carbons which were down, that means away from me, whereas bromine is towards me. Here two hydrogens are anti, so it will have greater rate. Whereas if you look at compound A, it has only one hydrogen which is anti to that of bromine, this hydrogen. On this beta carbon, you have hydrogen on the same side of bromine. So this hydrogen will not undergo elimination. This hydrogen, no elimination. No elimination, as it is not anti to that of bromine, which is going to be lost. So you should not think like this methyl and bromine, they are opposite, so they have less stereo repulsions. Methyl and bromine on same side, so they have more stereo repulsions. So A will undergo greater rate than B. That is how people also do commit mistakes. If you think of these two compounds, what are the compounds I have given earlier? Methyl and CH3, both are opposite direction. Methyl and Br, both are same direction. You will be thinking that methyl and bromine same direction, so that is unstable, so that will not be having great rate like that. But that is wrong. It's not about the repulsions alone, because the transient state looks like the alkene. So we have to compare the rate based on the stability of respective alkene, and the elimination is always anti-direction. So we have to look at number of hydrogens available which can undergo anti-elimination. These are very logical and critical points. Although you feel difficult at one point of time, you don't think like that. You try to develop the concept, you will understand it, you will enjoy it, you will score good. Am I clear, students?
Yes.
Yes.
Yes, sir.
So this is what E2 elimination means: anti-elimination, and 3 degree greater than 2 degree greater than 1 degree. And then you will be having respect to alkene transient states. And then there are some set of conditions, exceptions I have told you, where Hoffman's product is obtained. Conditions under which? Conditions under which Hoffman's product is major. The first condition, in the case of bulky bases, if the base, whatever you are considering tertiary butoxide is a bulky base, it can't pick up the proton from the in such a way such that more substitute alkenes are obtained. It will pick up the proton in such a way such that you will get the terminal alkene. So in the case of bulky base, first case. Second, conditions under which Hoffman's product is major. In the case of bulky base, the second condition is in the presence of poor leaving groups. Third, in the case of poor leaving groups, you can take fluorine, NR3 plus, SR2 plus. And third, in the case of extended conjugation. Okay, I have just given the names as of now. So in the case of bulky base, in the case of poor leaving group, in the case of extended conjugation, what are these points? I'll discuss in the next class with examples. After that, we can go with the even elimination. And the isomerization reactions and rearrangements, you can discuss as and when required. Like in specific parts, we'll have different types of name reaction. Those reactions we'll discuss as and when required. So after covering these exceptional cases where Hoffman's product is obtained major, and after looking at even elimination, we'll then proceed with your qualitative analysis, quantitative analysis, and purification. Right? Thank you all, everyone. Bye.
Thank you. Thank you, sir.
Thank you.